You know how they say the shortest distance between 2 points is a straight line? Well, in the world of logic and math, that's not always the case. Sometimes, the most direct way to prove something is true is to be completely indirect about it. In fact, sometimes the smartest way to prove you're right is to start by assuming you're wrong.
It sounds like a total riddle, right? But believe it or not, this is one of the most powerful tools a mathematician can have. Today, we're going to see exactly how it works by tackling one kind of odd mathematical puzzle using two different indirect methods. All right, here's our game plan. First, we'll lay out the puzzle we need to solve. Then, we're going to crack it using a really cool technique called proof by contradiction. After that, we'll solve it all over again with a slightly different method, proof by contraposition. And finally, we'll see how these two clever paths lead us to the very same truth. So, what is this puzzle we're going to be playing with? Well, it's a classic little problem from number theory, which is all about integers and how they behave. Specifically, whether they're even or odd. So here it is. For any integer m, if 2m plus 7 is divisible by 4, then m is odd. Now, you could try to prove this head-on. Start with the if part and try to wrestle the algebra into proving the then part. But honestly, that can get messy and fast. So instead, we're going to take the scenic route. First up is method 1. Proof by contradiction. And the name really says it all. The whole goal is to create a contradiction, a logical paradox that just can't exist, which in turn proves we were right all along. Think of yourself as a detective. You have a suspect, and the suspect gives you an alibi. You say, okay, let's assume your alibi is true. But if you follow that alibi and it leads to the suspect being in two places at the exact same time, well, boom, that's a contradiction. The alibi has to be false. We're about to do the same thing, just with numbers instead of a suspect. So, step 1, we state the total opposite of our original statement. We assume that there is some integer m where two things are true at once. First, that 2m plus 7 is divisible by 4, and second, that m is even. This right here is our suspect's alibi. We're assuming it's true and seeing where it leads. Now, we just follow the logical breadcrumbs. If m is even, we can define it as 2k, where k is just some other integer. And if 2m plus 7 is divisible by 4, we can say it equals 4j for some integer j. Now for the key move. We substitute that first piece of info into the second. That gives us 2 times 2k plus 7 equals 4j. A quick bit of simplifying and we land on this equation. 4k plus 7 equals 4j. Okay, just take a look at this. Right here. In this simple little equation is the fatal flaw in our alibi. Do you see it? Think about it. 4k is even, 4j is even. Can an even number plus 7 equal another even number? Let's make it even more obvious. Let's just shuffle the equation around a bit to get the numbers on their own. We'll subtract 4k from both sides, which gives us 7 equals 4j minus 4k. Okay, now let's just divide everything by 4. And we get something really, really weird. 7/4 is equal to j minus k. And there it is, the contradiction. See, j and k have to be integers, right? And if you subtract one integer from another, the answer must be an integer. It could be 10, it could be -3, but it can't be a fraction like 7/4. That's just impossible. Our alibi led us to nonsense, which means the alibi was false. And if our assumption was false, the original statement has to be true. Case closed. Okay, that was one way to crack the code. Pretty cool, right? But there's another, often more, elegant way to do this. It's called proof by contraposition. So let's reset the board and try solving this puzzle a whole new way. Now, the logic here is a little bit of a mind bender, but it's super powerful. Any statement that says if P, then Q, is logically identical to a rearranged version called the contrapositive, which says if not Q, then not P. They're like two sides of the same coin. So if you can prove one is true, the other is automatically true as well. So let's see how this works with our puzzle. The original is, if 2m plus 7 is divisible by 4, then m is odd. To get the contrapositive, we flip it and negate both parts. That gives us our new mission. Prove that if m is not odd, which just means m is even, then 2m plus 7 is not divisible by 4. Let's see if we can prove this new statement. Okay, so we're starting with our new assumption. M is an even integer. And just like before, that means we can write m as 2k. And, just like before, we plug that into our expression, 2m plus 7. And look at that. we end up with 4k plus 7. This all looks very familiar, but remember, our goal is different this time. We have to prove that this expression is not divisible by 4. To do that, we need to bring in a special tool. And here it is, the quotient remainder theorem. Now, this sounds super formal, but it's actually something you've known since you first learned division. All it says is that when you divide one integer by another, you get a quotient, the answer, and a remainder, the leftover bit. For something to be perfectly divisible, that remainder has to be 0.
So let's use this idea on our expression 4k plus 7. We want to know what happens when we divide it by 4. We can do a clever little trick here. Let's rewrite the number 7 as 4 plus 3. Now our expression is 4k plus 4 plus 3. From here, we can factor a 4 out of the first two terms, which gives us 4 times the quantity k plus 1 plus a leftover 3.
And that is the crucial point. Look at that form. 4 times something plus 3. It perfectly matches our theorem. 4 is the divisor, k plus 1 is the quotient, and 3 is our remainder. Since that remainder is 3 and not 0, we have just proven that 2m plus 7 is not divisible by 4. And because we proved the contrapositive, we've also proven the original statement is true. Awesome.
So there you have it. We took one puzzle, went on two totally different logical adventures, and both times we ended up at the exact same destination: the truth. Now let's just take a moment to put these two methods side by side.
This table really breaks it down nicely. With contradiction, our starting assumption was that the entire statement was false. Our goal was just to follow the logic until it blew up in our faces, which it did with that integer equals fraction impossibility. But with contraposition, we had a much more targeted mission. We only assumed the second part was false, and our goal was to prove that this forced the first part to be false too.
Proof by contradiction feels kind of like setting a trap and just waiting for logic to fall into it. Proof by contraposition feels more like a direct argument, just aimed at a slightly different, easier target. Both are incredible tools for thinking, proving that sometimes the cleverest path to the truth isn't a straight line at all. So which one do you think is cooler? Which one feels more powerful to you?